Hello, everyone. This is the lecture for section 7.1, Solving Trigonometric Equations with Identities. Okay, so uh, up to this point, we have covered, in terms of trig, right, we've covered angles. We know what sine and cosine and tangent are. We know what secant, cosecant, and cotangent are. We graphed 3 of the 6, right? And we got to sort of play around with the trigonometric functions, right? Okay. Section 7.1 is one of the heavier hitting, like heavily mathematical sections. Okay. Um, the stuff that you're going to see in this section, you will see more of if you do math for the rest of your life, if you do physics for the rest of your life, and if you do the higher end chemistry for the rest of your life. Okay. So what we're going to do is there are a certain number of what we call trigonometric identities, okay, that hold true for any angle that you put into them, okay? And then we're just going to play around with those like a lot, okay? So the first thing I want to define is what the heck is a trigonometric identity? Like I said, it is an equation. It is a statement that will hold true for all values or variables in the equation, okay? So I've got a couple down here. Okay. Uh, let's take this first one, right? If you take a look at this, right, we have on the left-hand side, we have 3x. And the right-hand side still stays the same, right? So if we solve this out, minus 2x, we get this. X is equal to 2. Bam, right? Okay. This is not an identity. No, nope, nope, nope. Okay. Now, the reason why it's not an identity is because the left-hand side is equal to the right-hand side only when this is true. Only when x is equal to 2. Okay? So, in order for it to be an identity, it needs to be true for anything that I can possibly plug in for x. Correct? Got it? Okay. The next one down, right? If we do the same thing on this left-hand side, we get 3x is equal to 3x. Okay? Notice that in this case, right, it doesn't matter what I plug in to x, the left-hand side is always going to be equal to the right-hand side. Got it? So this is an identity. Ugh, nasty D, there we go. Okay? Next one down. So if I do, let's see, minus 2x, right? Minus 2, we get left with minus x is equal to minus 1, so x is equal to 1. Nope, not an identity. Okay, so what I mean here, right, is this, right? That this left-hand side is equal to this right-hand side, right? Only at x equal positive 1. Makes sense? The left and the right are equal only at x equal positive 1. Not at any number x, right? Only at x equal 1, because we were able to solve it out. And that's a good way to figure out if you have an identity or not. If you solve it out and you get just one single solitary answer, or just finite number of answers in our case, right? Then you do not have an identity. Okay, an identity has to work for everything, everything. Okay, D. Okay, if you look at the left-hand side, right, this is 2x plus 2 is equal to 2x plus 2. Again, right, this thing works for any value of x that I want to put into it. So we have an identity. Okay? Okay. E and F. Both of these, let me put this. Okay? E and F. Both of these are identities. Okay? So one of them should look familiar to you. This one, the bottom one. Okay? if you take a look at this thing, right? If you take a look at the thing that's inside, right? You should notice that for f, it looks like sine squared plus cosine squared is equal to 1. That is our Pythagorean identity, right? Yeah. So technically, it doesn't matter what this is, right? So long as it's the same, because that's what the identity says, right? It can be whatever it wants, whatever it wants. So sine squared plus cosine squared is always equal to 1, right? This is one of our Pythagorean identity. This is the Pythagorean identity, right? Since the Pythagorean identity works for any angle I put into it, right? It is an identity, okay? Okay, this one is an identity, but we haven't covered it yet. This one's an identity, we haven't covered it yet. This is gonna probably show up, I think it does show up, in section 7.2, okay? And as a matter of fact, the rest of chapter 7 is gonna be me providing more identities for you to use when you're figuring out trigonometric stuff, okay? Okay. These right here are a handful of big ones. Okay, some of these we've already seen, right? So here's our trigonometric or our Pythagorean identity, at least the first one, right? All of these other ones, that one and that one, they're based off of that first one that's in yellow. Okay, if you guys remember from chapter 5, we've done all of these. I know it was a long time ago, and we only did it once, but we did them. Okay, even in odds. I sort of gave a little bit of theory of how this turned out, right? Okay, and then we have some of these cofunction ones. Somebody has mentioned in the class that you can grab a sine graph, right? Move it either left or right and get the cosine graph, right? And vice versa. You can grab the cosine graph, move it left to right, and get the sine graph, okay? So these are all the identities that we have already seen, okay? And I will not require proof for these, okay? Don't worry about proving these at all. You can just go ahead and say, I know these, and I can use them outright, okay? But now, the reason why we have to cover identities is because with a lot of trig functions, right, with a lot of trigonometric expressions that we can write down, we can equate certain versions of trigonometric expressions to other trigonometric expressions, okay? Essentially, what we can do with all of this stuff here is find and prove other trigonometric identities that are not stated, okay? Okay, so what do I mean by that, okay? In terms of proving trigonometric identities, right, let me at least just go through the game plan, okay? There are 4 big rules. Okay, let me not say rules. There are 4, I guess, primary methods to show that one certain trigonometric identity is equivalent to another. Okay, the first one. Okay, and the second. Let me do first and second. Okay. What you want to do here is either grab the left-hand side of your expression and turn it into the right, or grab the right-hand side of the expression and turn it into the left-hand side of the expression, okay? How you want to do that is up to you. It is up to you, okay? Those are the first 2, those are the primary ones that get used, okay? The third one, okay? This one's one of those, like if you get stuck on both the left and the right, you don't know what to do, maybe you can get it into a common spot. That's number 3. Okay, you can either grab the left-hand side and the right-hand side, okay, and whittle them down. Work with them on both sides till you get to one common expression. So if you can reduce everything on the left and everything on the right to something that looks the same on both sides, that is equivalent to proving a trigonometric identity. Okay, and then the last one happens more often than not. That's why I wanted to put it in here, right? You can grab the entire expression, either the left and the right, right, and turn it all the way down into a known trigonometric identity, okay? What do I mean by that? You can grab both the left and the right. And if at the very end, you're playing around with the stuff, right? You're playing around with sines and cosines. And at the very end, you get down to sine squared plus cosine squared is equal to 1. That is a known trigonometric identity. That is the Pythagorean identity, right? If you get that, you're done. You have proven the trigonometric identity from the beginning. Okay? Okay. What I do want to sort of point out, okay? What I do want to point out when proving a trigonometric identity, okay, is this. It's the fact that the very next line down, right? You can use any mathematical trick or any trigonometric identity that you want. That's already been proven to your advantage. You can prove a trigonometric identity however you want. Okay. Some tricks that we can use. Okay, let me actually point these out first. You can multiply by 1 or add 0. Okay, this is not foreign to everybody. Okay, if you remember when we did common denominators, right? We had to multiply the top and the bottom by the same number in order to get a common denominator, right? We were multiplying by 1 essentially there, right? Okay, so that's a trick that you can use. You can add 0, okay? In anything, you can go ahead and add 5 and then take it away. That's adding 0, but if you need the 5 and then subtract the 5, but you need them grouped up with specific things, then more power to you. You can do that. That is perfectly fine, okay? Use some common trig identities. Like I said, I gave you a couple from up above. That is perfectly fine, right? Common denominators, sometimes you might need to do common denominators, right? Or conjugating an expression. Hopefully you guys remember the conjugate of an expression or of a number. If you don't, I believe it's section 3.1 where I show you how to do a conjugate, okay? At least a complex conjugate. But the idea for conjugating an expression is no different. You just change that value in the middle, okay? Okay. The thing that I really want to impose on everybody here, okay, is this. The idea behind proving a trigonometric identity, okay, is that we are now looking at your arguments, okay? The mathematical process of proving something, right, is now secondary, right, to your logic, okay? We need to make sure that when we prove trigonometric identities, that your arguments hold water, okay? You can use any math you want, but the argument for why every step is the way it is, that's now on the table, if that makes any sense, okay? Okay, enough talking, right? Look at me go. 2, this should be 3. Okay, so let me do this first one, okay? I want to prove that this right here is equal to 1, okay? Like I said, I can use any method I want. I can use any method I want, okay? So here we go. And I think I'll leave this up here. I'll mention it here. I think I'm going to want to do these in class. I'm pretty sure a lot of you guys aren't going to look at the video before I cover this, so it's going to be healthy for us to do this. It's going to be healthy for us to do this in class with everybody, okay? It's going to be a, sort of like a, I know this is going to sound horrible, but sort of like a joint frustration for everybody. That's fine, okay? Okay, without further ado, how do I prove this identity, okay? So I can use any one of these 4 things I want, these 4 methods right here, okay? I would suggest using the more messy version, okay, to make some headway into this, okay? So in this case, okay, I am going to use the very first option. I'm going to grab the left-hand side of the expression, this side, and make it equal to the right-hand side. So I'm going to try to grab all of that left-hand side and make it equal to 1. okay? But I get to use my trig to do it, okay? So, to start, so I'm going to try the very first item, the first of our strategies here, up here, okay? I'm going to grab the left-hand side and try to turn it into the right-hand side, okay? So I'm going to try to grab all of this and make it equal to 1, okay? So like I said, I can use any one of all of these mathematical sort of tricks that are up, sort of cheap parlor tricks that are up your sleeve, right? You are allowed any and all of them, right? So long as you do it right, okay? So I want to show you guys this, okay? For both of these, this one and this one, right? If you recall for the first one, this one over here, right? Let me actually start with the beginning. Sine squared of x plus cosine squared of x is equal to 1. Okay, this is our vanilla Pythagorean identity. Okay, now look at this. I can do minus cosine squared of x, right? Minus cosine squared of x. So I get this. Sine squared of x is equal to 1 minus cosine squared of x. Okay, now I am going to highlight that in yellow because that's going to be important in a second. Okay, I can do the same thing. Well, actually, not the same thing, but it's already there. So if you go back up into the fundamental trigonometric identities that I provided just a couple seconds ago, right? We have this 1 plus cotangent squared of x, right, is equal to cosecant squared of x. Okay? So, now what I want to do is this. I'm going to go over this way, and I'm going to do this. 1 minus cosine squared of x times 1 plus cotangent squared of x, right, is equal to, we know what this is, right? That is going to be sine squared. Okay? And let me highlight this because this is the other important thing, and I'm going to highlight it in pink to differentiate it, right? That was from here, over here, right? And then this is from right here. So we have this, sine squared times cosecant squared of x, okay? Okay. Now I'm going to use my cosecant identity, right? So sine squared of x times, cosecant is 1 over sine. You guys remember that? So it's going to be 1 over sine squared of x. And if you multiply both of these together, you get 1. Bam. Quatus erratus demonstratus. That which was needed to be proved. I believe that's what it stands for in Latin. Basically says we have proven the thing we wanted to prove. Okay? Notice how I did it, right? Every single step had to be explained. I could use whatever mathematical trick I wanted, but every step was explained. Got it? Okay, let's try out another one. Okay, I am again going to try the first one. I'm going to try grab the left, turn it into the right. Okay, just to give you guys sort of a little bit of practice. But I will say, actually, no, I'll take it back. I'm going to try the right-hand side and turn it into the left to show you guys that you can do it that way. Okay, now I believe for this one, you can do the left-hand side, turn it into the right. It will work. Okay. But I'm going to do it just for sort of educational purposes, right? I'm going to do the right-hand side into the left. Okay, so I'm going to start with that right-hand side. I'm going to start with cosecant of x minus sine of x. Okay, and I'm going to try to turn it into this right here. Okay, I can use whatever I want. Okay, any identities, any mathematical trick that I have up my sleeve, I can use. Okay, but I have to do it right, and I have to get this out, right? I have to get it equal to that. Okay, so here we go. Cosecant is 1 over sine, correct? So 1 over sine of x minus sine of x. And I'm going to do over 1 because I can do that. I can do over 1 with whatever I want, right? Okay. It looks like I'm going to need to do common denominators here, right? So you see how one of these has a sine of x on the bottom. So I'm going to do times sine of x here times sine of x here. See, look what happened. I am multiplying it by a 1, right? It's just a nice one because I needed to, right? So 1 over sine of x minus sine squared of x over sine of x, right? This I can combine to this, right? I can combine to 1 minus sine squared of x over sine of x. Okay? Okay, I'm going to put this down here. 1 minus, I'm going to do this again. Sine squared of x plus cosine squared of x. That is equal to 1. You guys remember that, right? Now, I'm going to try to get this expression out somehow. I need 1 minus sine x. So that means I can grab my minus sine squared of x minus sine squared of x. Cosine squared of x is equal to 1 minus sine squared of x. You guys see this identity that I just produced right here, right? Look at this. Right? So now I can use that up here. So this is equivalent to cosine squared of x over sine of x. Okay, we're getting somewhere. We're getting somewhere, right? Okay, so now, if you guys recall, right, this is something that we can do with fractions, right? Cosine squared is cosine of x times cosine of x over sine of x. There's nothing wrong with that. Okay? Let me grab this because I do want to do. I'm going to put it right here. Okay? Because I need something else after this. Okay? So what I want everybody to look at is this. Secant of x is equal to 1 over cosine of x, right? This is one of our identities, right? So then I can say now, right, 1 over secant of x is equal to cosine of x. And if you need to do it, work it out. If you put a 1 down there and multiply everything out, this is the next identity that we're going to get. Okay? This one, I'm going to use on this one. Okay? But first, before I do that, I'm going to grab that one and separate it away. Times cosine of x over sine of x. Okay? And I'm going to highlight the thing that I'm hitting it with, right? So that's the purple cosine that I'm going to use my identity on now, right? This is now equal to, cosine is 1 over secant, 1 over secant of x times cosine of x over sine of x. And if I multiply this using multiplication of fractions, right? You guys hopefully see cosine of x over secant x sine x. And look at what we just did. QED. Quadratus Eratus Demonstratus. Okay, so notice what I did. I started with the right-hand side, right? And I reasoned out through trig, right? I reasoned out that it is equal to the left-hand side. Got it? Okay. Like I said before I started this one, if you do it the other way around, if you do the left-hand side, make it equal to the right-hand side, that's also going to work. Okay. I think that one is actually the easier method to do it. Okay. I just did it, grabbing the right, turning it into the left, just for pedagogical reasons, so that you can see that you can do it in either direction. Okay. Okay. Next one down. Prove this identity right here. Boom. Okay. Like I said, right? You can start with the left, turn it into the right. You can grab the right, turn it into the left. Okay. Grab them to any common identity. So if you get the right and the left and make it equal to the same thing, that counts, right? Or turn it into a trig identity that you already know. That's perfectly fine, right? More often than not, you really want to start with the most messiest side, okay? Hopefully you guys see what I'm talking about here. It looks best. I have more options, more stuff to play around with. If I grab this side, the left-hand side, and turn it into the right-hand side. You guys see that? I got more to play with. I got more stuff to play with if I do it that way, right? Even myself right now, right? I don't see how the heck I'm going to grab cotangent and break it up into this. Does that make sense? Okay, so I usually tell this to everybody, start with the messier side, okay? Usually things simplify out very nicely, okay? So I'm going to grab the left-hand side. I'm going to grab this, right? Cosecant of x minus cotangent of x all over secant of x minus 1. I'm going to grab that side and turn it into cotangent. So hopefully something will happen that everything will go away and you just get left with cotangent. Okay? So as I stated from up above, right, the easiest thing you can do with all of these is grab all the sines and the cosines, or sorry, grab all the trig stuff and just change them back to sines and cosines. Okay? Cosecant is 1 over cosine of x minus cotangent is cosine of x over sine of x divided by secant is 1 over cosine. Oops, look at me go. Cosecant is 1 over sine. And secant is 1 over cosine of x. Who caught that before I actually finished writing it down? Okay. You guys see what's happening up top here, right? Before I do anything with the top, I'm going to play around with the bottom. See this 1? I'm going to do common denominators. Okay, so I'm going to write the top out again. 1 over sine of x minus cosine of x over sine of x. That's just me rewriting. I'm not doing anything special with it. So this one I'm going to do 1 over cosine of x, right, minus cosine of x over cosine of x. Okay? So notice we have a bunch of fractions inside of a bunch of fractions. Right? Okay. With the top, I can combine this way. 1 minus cosine of x over sine of x. Got it? And with the bottom, I can do 1 minus cosine of x over cosine of x. Okay, so hopefully you guys realize here that we have a fraction of fractions, right? Back in the day, we knew how to play around with this, right? We rewrote it, 1 minus cosine of x over sine of x divided by 1 minus cosine of x divided by cosine of x. Okay, if we wrote it out this way, this is the division of fractions, right? So we can grab the second one, flip it, turn it into a multiplication. Okay, so this means I have this now. 1 minus cosine of x over sine of x times cosine of x over 1 minus cosine of x. Okay, now look at what happens. We have a 1 minus cosine on top that's being multiplied to a 1 minus cosine on the bottom. They are going to cancel. And I get left with cosine of x over sine of x. And if you remember, cosine divided by sine, cotangent x. Ta-da! Q-E-D. Quadratus erratus demonstratus. We showed what we needed to show. We had to grab this side, right? We had to grab the left-hand side and turn it into the right-hand side. And that's exactly what we did. Whew. Hopefully that makes sense. This takes a long time. I'm going to give you guys another couple things that you need to just worry about. But I want to do that in class. Okay. What I have coming up next is a couple of verify following trigonometric identities. There's actually going to be 2 for each one for you guys to do. Okay. Everybody's going to be doing 2. Every group's going to be doing 2. This is going to be the first one. And this one's going to be the second one. Okay. Solving trigonometric expressions using algebra and the identities. Okay. For now, I'm not going to make these too much more difficult. Okay. We are going to be using identities, but I'm going to keep them simple for right now. Okay. So we know what trig functions are. We've played around with them as functions. We've graphed them. We haven't solved trigonometric expressions entirely, not completely yet. Okay, so that's what I want to cover here. So suppose you have, I'm going to start with B. Suppose you have something like this. Okay, I want to find the x values. I want to find these x's. Okay, such that when you do square root of 2 times sine of that angle plus 1, it's going to be equal to 0. Okay, I want to find all of those x values. Okay, turns out some of these you can do by the unit circle. Okay, so here's what I mean. I want the sine x by itself. I'm going to try to get this sine x by itself. So minus 1, minus 1. So I have square root of 2 sine x is equal to minus 1 divided by the square root of 2 divided by the square root of 2. This is saying, whoa, this is saying sine of, some angle x is equal to negative 1 over square root of 2. And if you guys remember how to do these, this is the same thing as saying negative root 2 over 2. Okay, so now think about your unit circle. Okay, pull it out if you need to. Okay. Sine is equal to negative root 2 over 2 at 2 angles. So that means x is going to be the first angle if you go around the unit circle, right? That is going to be 5 pi over 4. Okay, and the next time that happens, 7 pi over 4. So we solved it out. Bam. Okay, simple enough, right? Simple enough. Okay, now you could do the sine inverse of stuff, right? And the calculator is going to give you a decimal number. Okay, if you can recognize that that is root 2 over 2, more power to you. Okay, now, you do have to show me that it is equal to negative root 2 over 2 or positive root 2 over 2, whichever one it is, okay? Just keep that as a warning. The online system for your homeworks is also looking for the same thing, okay? It wants the exact version. And in this case, I'm going to be looking for the exact as well. So I'm looking for that, okay? Okay, let me increase the difficulty now, okay? Let's say we had this, okay? So this is actually something that you've already played around with. This is the first time you'll see it used in this manner. Okay, so watch this. Okay, minus cosine theta plus 1 minus cosine theta plus 1. So we have this going on now. 2 cosine squared of x, right? Minus cosine of theta. Whoops, that's supposed to be a theta. Plus 1 is equal to 0. Okay, now what I want everybody to see is this. If I make this, I'm going to do a, this is going to be a, you're going to be expected to be able to do this, okay, on the fly. Not right now, but sometime in Calculus 1, this is going to have to happen, okay? This is the first time I'm going to show it to you, okay? I'm going to make u equal to cosine of theta. So that means this is what happens. 2u squared minus u plus 1 is equal to 0. Okay? Okay. This turns out it is equal to 2u plus 1, u minus 1 is equal to 0. Okay? Did I screw that up already? I did. Look at me go. Okay, I've got a correction that I need to make. Plus 1, so this is minus 1, minus 1, minus 1. My bad. Make that change in your notes, please. Okay, now it's equal to it. There we go. Woo! Okay, now, you guys see this? U is equal to cosine theta. Okay, I'm going to resubstitute everything in. 2 cosine theta plus 1 cosine of theta minus 1 is equal to 0. Okay, so if you guys remember, right, when we have two things multiplied together equal to 0, we can break them up. I can do 2 cosine of theta plus 1 is equal to 0, or cosine of theta minus 1 is equal to 0. Okay? If you solve each one of these separately, I'm going to actually do this. Okay? If you look at your unit circle, right, the first one is going to be these. 2 pi over 3, 4 pi over 3. This one will produce these two answers. Okay? And the second one is going to produce 0 and 2 pi. This one is going to produce these answers. Okay? So sum total, there's going to be 4 answers. Okay? Whew. All right. I know this is amped up in difficulty, okay? So just follow along, okay? I'm going to do a lot of practice on this in the next couple weeks, Okay. Quick checks. I've got a couple there, and then after that, it is lecture questions. Okay. If there's any questions on the stuff that I just covered, please ask me during our quick check time or during my office hours. Okay. Besides that, happy studying.